Hi everyone, this is video 6, and today I'll be talking about approaching coding questions. This video is going to have a little bit of a different flavor than the previous videos in that today I won't be going over as much new material, but more so I'll be doing a lot of coding examples and questions that you might see, and what I'll basically be doing is going through all of these examples, some of them of various difficulties, and some of them you'll find quite easy, some of them you'll find a little bit difficult, and others you might find very challenging. So I've included all types of difficulties, and I'm going to go over all of these types of questions so that you see how I approach programming questions, and hopefully you guys can get a few takeaways from all of this. But before I start with the questions, I want to briefly talk about a subject that I've mentioned here and there, mainly errors. And there are three types of errors that you'll see in Python: syntax errors, exceptions, and logic errors. And now I'm just going to go through examples of all of these. So if we open up command prompt and just run Python, so the first example is a syntax error, and you guys might have done a lot of these when you've practiced coding. Basically, for example, if I have an if statement, and usually I put a colon right at the end of this. If I don't put a colon, bam, I get an invalid syntax. So this is basically what a syntax error is. You mess up the syntax. Okay, so pretty intuitive. And the next type of error, we've already seen a couple of these. If we divide by 0, we get an exception. It's called a zero division error. Okay, so this is part of a special class of errors. We'll be talking about this a little more when we talk about error handling. But basically know that exceptions are runtime problems. Okay, so it realizes the program has a few problems that can't run. Okay, now another type of error that you might get is, let's say I define a function and I want to return x times x. So this is our favorite function, square. Let's say I call this function, instead of doing square of 5, I accidentally put another argument. So this causes a different type of exception called a type error. And these errors are honestly pretty easy to handle because Python basically tells you exactly what's wrong. Zero division error, division by 0, line 1. It even points you to a line. So it's pretty nice. And so these types of errors you shouldn't have too much problems with. But now I'm going to talk about another error called a logic error, and these are a little bit tricky sometimes. So, remember from last time we had this function called middle. It basically returns a middle value in a set of 3 numbers, and we used logic operators to do this. Now, let's say while I was defining this function, I made a mistake, and instead of having an AND operator here, I put an OR operator. A simple mistake, but let's see how exactly we would go ahead and fix this mistake. So the first thing I would do is, obviously you want to check that the function is right, and to do this we run a doc test. And so this is why testing is so good, because now the doc test tells us exactly what's wrong. So whenever we have an error in logic, hopefully the tests catch it, and then you can see exactly what's going on. So now let's figure out what's going on. So here we have middle, -2, -10, and 10, and we're expecting -2, which is the middle number, but we get -10. And here we're expecting -1, and we got 3. So immediately we can see a pattern here in that for some reason the function is always returning the second value. So here it returned -10 instead of the first value, and here it returned 3 instead of the third value. So where is it that we're returning the second value? Oh hey, return B. So now, immediately, we can isolate our error to somewhere in this if statement, because this if statement is wrong because it's always returning B. So now let's see if we can figure this out. So we go through if B is greater than A and B is less than C, or B is less than A. Oh wait, this should be an AND. And there we go, we found our error. And then now, we'll test it again, and it works. So this is how you basically go about this process is called debugging, and a logic error informally is known as a bug, and debugging is the process of fixing the bug. And so that's what I've just done here. Debugging can sometimes get very difficult, but if you have good tests that catch your logic errors and you test frequently and often, you should be fine, and you'll find a lot of these bugs as you go, and it's a lot easier to find a bug if you've only written a little bit of code rather than writing a giant amount of code and trying to find a bug in like 100 lines of code. It's very tough sometimes. So make sure you test often. Okay, so now let's go into the examples. So these first 4 questions, really 3 questions, but with a bonus question at the end. But these first 4 questions are pretty straightforward, and I want you to take some time and see if you can figure them out. And it's okay if you can, because this is just going to be practice. So take some time, and I'm just going to go straight through these examples. So we have a factorial of a number, we want the nth Fibonacci number, and we want a function that calculates the summation. And at the end, we have a bonus where can you write this function in 1 line? Alright, so let's start writing code. So, the first function we want to define is the factorial. So, what is a factorial? Well, we just return 1 times 2 times 3 times all the way up to n. That's a factorial. And so now let's do some doc tests. So the first factorial to know is that factorial of 0 is actually 1. Factorial of 1 is obviously 1. And then factorial of 3 is 6. So I'm going to write throughout this video where I'm writing functions, I'm going to make sure I write extensive tests because we want to make sure that these functions are right. And then factorial of 8 is going to be 40,320. Alright, so there's our doc test, and now I'm going to start writing code. I'm not going to do test-driven development in this video. So you saw a couple of examples of me doing test-driven development in the previous video. So I'm just going to go straight into it. Okay, so when we're doing factorials, we start at 1, and we multiply by 2, multiply by 3, multiply by 4, all the way up to n. So already we can see that we're going to need a while loop. Okay, and so we're going to need some type of counter. I always like to call my counters I. And as long as it's less than or equal to n, because we go from 1 to n, we're going to basically have some result. And each time we're going to multiply the result. We don't know what the initial result is, but let's just get a framework for our solution, basically. So we're going to do result is equal to result times I, right? And then every time we're going to increment I. So we know this is going to be the general format of our solution. And now we got to figure out, hey, what's our initial I? Well, we start at 1, so we can have I is equal to 1. And then what's our initial result? So now, first of all, we know that we're going to return result at the bottom here. So now we got to ask ourselves a question. Hey, if this while loop did not execute, what should the result be? And that will give us insight on how to figure out what the result exactly is initially. So, what's the only case in which factorial of some number is not going to execute this while loop? Well, it's the case that I is not going to be less than or equal to n. And what's the only number that does that? Well, that's going to be factorial of 0. Awesome. So our initial result is going to be 1 because factorial of 0 is initially 1. And now once we have this, we have a function. So now let's test it. And it works. Alright. So notice how I started with the while loop because I knew that's something that was necessary, and then I basically started with the while loop and worked through that to figure out the rest of it. So the next function we have is our Fibonacci, calculating the nth Fibonacci number. So calculates the nth Fibonacci. Don't know if I spelled that right, but whatever. So what's the Fibonacci series? We have 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. So that's our that's the first 10 Fibonacci numbers. And for the purpose of this problem, I'm going to say this is the first Fibonacci number, this is the second Fibonacci number, third Fibonacci number, and so on. So if I call fib of 1, I'm going to return 0. If I call fib of 2, I'm going to return 1. If I call fib of 3, I'm going to return 1. And then if I call fib of 6, I should get 5. And then if I call fib of 8, I should get 13. So let me scroll down here. And then if I call fib of 10, I should get 34. Alright, so now let's figure out how we can do Fibonacci numbers. Okay, so in order to do this function, we really have to know what exactly the Fibonacci series is and how we calculate it. So the way we calculate it is the Fibonacci numbers have some two initial numbers. And in this case, it's going to be 0 and 1. And every single number after those two initial numbers is going to be the sum of the previous two numbers. So here, 1 is 0 plus 1, 2 is 1 plus 1, 3 is 1 plus 2, and so on and so forth. Okay, so we can use this idea and translate this into code. So what are our two initial numbers? So I'm going to call them previous and current. Okay, and I'm going to initially set them to 0 and 1. That's exactly what they are. And now, as with all of these examples, we're going to have some case where we need to keep track of our Fibonacci numbers while I is less than or equal to n. And what we're going to do is we basically need to check every time we go through, well, how does our previous and current change? Well, previous and current initially is going to be 0 and 1. And then after the first iteration, what we want to do is we want to have previous and current be the next one. Okay? And then after the second iteration, we want previous and current to be the next one. Okay, so now basically we have the idea of what we want to do. Now we want to translate this code. Well, every time, so now we want to redefine previous and current. So notice that in our first iteration, previous and current is 0 and 1. Then our previous variable is going to be the current variable of the previous iteration, and the current variable is going to be the previous plus the current. And this is basically how the Fibonacci series works. So previous is going to be current, and current is going to be previous plus current. Alright. And then each time, we're going to increment our variable. So I don't know what my initial value of I is so this is something we're going to figure out. But, so what do we return in the end? Well, now we have an interesting question. Do we return previous or do we return current? Alright, let's think about this. Well, let's look at our first case. If we call fib of 1, we get 0. Notice that current is never ever going to be equal to 0. Only previous is going to be equal to 0. So the only way that this function could possibly work for that example, is if we return previous. So notice that I'm really just using, I'm not really going into the details of why this is true, but with some simple logic here and there, I can figure out what I need to return. So I need to return previous. Okay. Now, what would be the case where previous would be 0? So my next question I'm trying to answer is, what should I set my initial value I, my initial counter I, to equal? Okay, so the only time I'm going to return 0 is if this while loop doesn't execute, right? And what's the only number n that causes this while loop to not execute? When n is equal to 1. Okay, so I need I to be something more than 1. And the smallest number that's greater than 1 is 2. So I has to start at 2. And so now that I have this, I have a functioning definition of Fibonacci. So let's test it, and it works. Alright. So the next function I'm going to define is sum naturals. And this basically, I'm going to define a docstring as always, computes 1 plus 2 plus 3 all the way up to n. Okay, so let's also write some tests. Now, another reason I'm writing tests for all of this is it already gives my mind to start thinking about how to solve the problem. When you think about the examples, you're already thinking about how to solve the problem. So that's why testing, again, is so good. So I'm going to start, so sum naturals of 1 is going to be 1, sum naturals of 3 is going to be 6, sum naturals of 10 is going to be 55, sum naturals of 100 is going to be 50-50. Alright, so here are my doc tests. So now we got to figure out, hey, how do we solve this? So one thing you all might have noticed is that this 1 plus 2 plus 3 all the way up to n is very, very similar to the factorial function. And these two functions are very similar, but there is a little bit of a catch here and there. So let's think about this. So again, remember how we started the factorial function? We know we had to start from 1 and go all the way up to n. So let's say we start at 1. And then while it's the case that I is less than or equal to n, we want to basically, in this case, we want to have a result that's equal to result plus I instead of multiplied by I, right? And then we want to, of course, increment our variable. And then we want to return the result. Okay, so now the next question is, what should the result be initially? Well, what's the case where this while loop would not execute? So notice that I'm asking the same questions again and again to solve these problems. And these are the same questions you should be solving you should be trying to ask and solve when you solve these questions. So let's think about that. What is the case where this while loop is not going to execute? And that's the only case where that's true, since we have I is equal to 1, the only number n that can go into this and cause the while loop to not execute, of course we're not thinking about negative numbers in these type of examples, is when n is equal to 0. And what is the result when n is equal to 0? Well, result is 0. So our initial result is going to be 0. Awesome. And there we should have a fully functioning implementation, and it works. Okay. So now the next question we have is, can we make better subnaturals? Alright, and the better subnaturals is basically writing this function in one line. Okay, so let me copy some of these doc tests. I'm only going to copy a couple. And then let me copy the doc string, of course. So, okay, and awesome. So we have a couple of doc tests, and all I need to do is just add a b in front of these. B, oops. Alright, so now I've written doc test for this function. And so the way to do this is, if you have knowledge of Gauss's formula for computing the sum of the natural numbers from 1 to n, this should be quite easy. And so the answer is n times n plus 1 divided by 2. And for those of you who don't know this, I will have a video that explains exactly why this is true. There's actually quite a lot of deep, cool mathematics behind this, and there are many ways to show that this is true, and I'll go through the three of them that I know. So this is very cool, and I'll definitely have a video that shows why this is true. But, so this is the answer to that, and let's just make sure our code works. Oh, what's going on? Oh, I have a typo. Okay, see? Testing catches all of these problems. And yeah, it works. Okay. So this is basically going through simple iteration problems. And some of these might not be so simple for those of you who started programming, but once you start to do a lot of practice with iteration, you'll realize that these are quite intuitive. And go over these examples several times. It's totally fine. When I first started programming, I struggled with these, but I guess from my perspective, I see them as a little simple. I shouldn't be calling them simple. I'm sorry about that, but so this is pretty good practice for iteration, and that's all I got for now. So now